Yes, doctor, maybe this slide.
Okay. So the characteristics of surfaces are very important in manufacturing for several reasons. That can be aesthetic reasons, that can be safety issues. We know that friction and wear depend on the surface characteristics, and surfaces will affect the mechanical and physical properties. In addition, assembly of parts is affected by the surface's properties. So, smooth surfaces are desired in a lot of applications, especially electrical contacts. This is why we should ensure that we have smooth surfaces. So, in order to characterize the surface, we can define first the surface roughness or surface finish. So the surface roughness is a measurable characteristic based on the roughness deviations. The surface finish is a more subjective term denoting the smoothness and in general the quality of the surface. In popular use, we and in general surface finish and surface roughness is the same meaning, but both terms are within the scope of surface texture. Now, how to measure surface roughness? If you look at the following figure, you can see how if you have a smooth surface, it will follow a straight line. So this is a perfectly smooth surface. But in actual case, what we have deviation from this smooth surface in the upward and downward direction. So we can have positive and negative deviations. Okay. Now, uh, as a measure of surface roughness, we can do integration over the whole length to get, in average, what is the value of the deviation from the surface. So a first way to calculate roughness is the following by using the following formula. The arithmetic average roughness is based on the absolute value of deviations and is referred to as average roughness. Why we take the absolute value? Because we have positive and negative deviations. So if we do not put absolute value, we might end up with a result of zero while we have deviation up and down. So we should take the absolute value to get the average roughness. And then if you do integration, we integrate over the whole length. So from 0 to L of the absolute value of deviation dx over the length. Now, sometimes if we don't want to do integration, we can do another procedure. And of course, integration is the most accurate method, but it is, to do this, we need to draw the graph and calculate by or graphical method or calculation the integration. Another method that can also be used is to take several points. We take a high number of points on the surface and we measure the deviation, and then we can say that the average roughness can be estimated as the average of this deviation. So it's summation from I to n of the absolute value of y over n, where will ri will have the meaning of average roughness, yi is the vertical deviation, and n is the number of points you included. Okay. Of course, higher the number of the point, better is more accurate is the roughness value of things. Now, what about surface integrity? Surface texture alone does not completely describe a surface. There may be metallurgical changes in the altered layer beneath the surface that can have a significant effect on the material's mechanical property. So the surface roughness, just consider the geometry of the surface. It will not look at the layer beneath the surface. While surface integrity consider the characteristics of this sublayer, surface integrity is therefore the study and control of this subsurface layer and the changes in it that occur during processing, which may influence the performance of the finished part or product. So, when you do any process, it's true that you are altering the geometry of the surface, the outer surface. Uh, but in real case, not only the geometry from the outside will be affected, but also you will have a thin layer at the surface that will have a change in properties, and we will see that this layer can be altered by different forms of energies. So first, this surface changes that are caused by the application of variable form of energy during processing. For example, one of the most common types of energy that will affect this surface layer is the mechanical energy. So when you do processes like forging, extrusion, and machining, these processes have as function to change the geometry of the work part, but also this mechanical energy can cause residual stresses in this sublayer, can cause work hardening of the material, and can cause cracks in the surface layers. So in this way, this mechanical energy will affect the integrity of the surface. Now we have many other energy forms that can affect the surface integrity. So first we have thermal energy, which can cause metallurgical changes, as in the case, for example, of recrystallization. We have seen before that if we heat a material up to its recrystallization temperature, we'll have formation of new grains, and the surface characteristics will change. We can also use thermal energy to form a heat affected zone, which is a non-melted area of metal that has undergone changes in material properties as a result of being exposed to high temperatures. This is the case, for example, when you do welding or when you have a high heat cutting process. In addition, the surfaces can also we can alter the integrity of the surfaces by application of chemical energy. For example, chemical energy can lead to corrosion of the surface or contamination of the surface. Furthermore, we have, for example, the etching process, which use a strong acid or mordant to cut into a material. So this can create a design incised in the metal. Other form of energy is the electrical energy, which can cause a change in conductivity or magnetism property of the material. So all these energy forms can affect the surface integrity. Now, concerning measurements of surfaces, we have, as we said, we have two parameters of interest, which are surface texture, which just considers the geometry of the surface, and it's commonly measured by the surface roughness. And we have the surface integrity, which deals with the material characteristics immediately beneath the surface and the changes to this subsurface that can result from the processes acting on it. Now, in order to measure surface roughness, we have several techniques. The first one is subjective comparison with standard test surfaces, and it's not a very accurate method. It is based on fingernail test. A second, the more accurate method is stylus electronic instruments. And the third one is the use of optical techniques like microscopes. So let us go over these methods. First, we have the subjective comparison. So in the subjective comparison, we have a set of surfaces of known roughness. And what we do is, if you have a surface by fingernail touching, so we can touch the surface and touch other surfaces with known roughness. When we feel that it's the same touch, then we can say that we have similar roughness and determine the roughness of the surface. But of course, it's a very subjective method and it's not very accurate, especially when you have small roughness. If you have very small roughness, it will be difficult to feel it by touch. This is why we have more advanced techniques as stylus measurements. In this case, the concept is similar to the fingernail test, but it is more scientific. In this case, electronic devices as a cone-shaped diamond stylus is traversed across the test surface at slow speed. As the stylus head is traversed horizontally, it also moves vertically to follow the surface deviations. So it can trap the deviations in surface by vertical motion. The vertical motion is converted into an electronic signal that can be displayed as a profile of the actual surface, or directly it can calculate the average roughness value. And we will see the setup of stylus instrument in following slides. So here you can see a figure of a stylus instrument. As you can see here, this is the head of the stylus. So as you are moving horizontally your equipment here, this stylus can undergo vertical motion depending on the roughness of the surface. This is clearly illustrated in the following slide. So here, as you can see, this is your work part. You need to measure its surface roughness. So if you have a perfectly smooth surface, when you move your stylus in the horizontal direction, you will not have vertical motion of the stylus head. On the other hand, here, due to the deviation from the nominal surface, as you move in the horizontal direction, you will have vertical motion of your stylus head, and this will cause deviations in vertical direction that can be trapped by an electrical signal that can be converted to readings. Okay, so you can draw the profile, or you can also measure the average roughness. So this is how, so it is, as concept, it's like the fingernail test, but it is more accurate because you are touching the surface and you are directly transmitting any deviation to be to your system. Now, the third part is optical techniques. For example, we can use a microscope with a digital camera and a motorized table. This system is also a very accurate method. It can give you a 3D view of your surface, and it can also allow you to draw the profile for roughness of your surface. So this method can see both, and it can look at both the surface roughness and the surface integrity. Now, concerning tolerances and manufacturing processes, some manufacturing processes are inherently more accurate than others. Most machining processes are quite accurate, capable of tolerances up to plus or minus 0.05 millimeter or better even. Now, for example, other processes are not very accurate, like sand casting, which are in generally inaccurate, and their tolerance are up to 10 to 20 times of those used in machined parts. So it depends on your final product, the final product you want to have. If the accuracy is very important, you will not use sand casting. You can use other machining tools. Or after sand casting, you can perform certain finishing operation to enhance the accuracy. So some processes are inherently capable of producing better surfaces than others. In general, processing cost will increase with improvement in surface finish because additional operations and more time is required to obtain increasingly better surfaces. And in general, we need several steps in enhancing the surface finish. We don't do it in one step. So first, we use a machining. For example, if you use forging first, it is already forging or extrusion is already has a high accuracy, and after this you use super finishing, which will give you better and better smoothness of your surface. So processes noted for providing superior finishes include honing, lapping, polishing, and super finishing. I will just give a brief explanation for each of these types. So first we start with the honing process. Honing uses a special tool called a honing stone in order to achieve a precision surface. The hone will be composed of abrasive grains that are bound together with an adhesive material. And in general, honing grains are irregularly shaped, and smaller is the grain size produced, smoother the surface of the workpiece will be. Now, concerning lapping, lapping is a machining process in which two surfaces are rubbed together with an abrasive material between them. And this process can be done by hand movement or using a machine. For polishing, polishing is the process creating a smooth and shiny surface by rubbing it or using a chemical action, leaving a surface with a high specular reflection. And finally, super finishing is also known as micro machining or micro finishing, and is one of the most accurate smoothing processes. It is achieved by removing just a thin amorphous surface layer left by the last process with an abrasive stone or tape, and this layer is usually about 1 microns of magnitude. So this is chapter 6, material. Now I prepared for you some problems on measurements of from Vernier scales, linear Vernier scales, and rotary Vernier scales. You have seen this in videos, and I will repeat this for you to, in case you didn't
Doctor,
understand. Yes.
can you repeat the first one, honing? The
Yes.
first process?
Yes. Honing consists on using if you want to take a stone, and this stone is made of small grains. Okay. The surface of it is made of small grains. So what you do is the hone is composed of abrasive grains that will be bound together with an adhesive material. And what you will do is that when you put the tool on the surface, يعني بتحفون على بعض, okay? When you do this, بصير surface will be smoothened by the grains, okay? So this is the idea. You have a tool with small grains on its surface. وقت نحف التول على الماتيريال due to they will take the small size, يعني due to the small size of the grains, this will lead to a smoothening of your surface.
Okay,
Okay.
doctor, thank you.
Okay. So now I will start with a new document for measurement using linear scale and rotary Vernier scale. I will pause the document for you on Blackboard. So you have seen in the videos how to read these Vernier scales, and I will repeat this to highlight more the idea. So first, the precision of length measurements can be increased by using devices that use a sliding Vernier scale. So we have two of such instruments that are based on Vernier scale, and we use a lot in labs, are Vernier calipers and micrometer screw gauge. These instruments will have two scales. We have a main scale in millimeters and a sliding or rotating Vernier scale. And in this case, for example, this figure here show a linear Vernier scale, as you can see. In this case, okay, the main scale reading will be the first reading of just to the left of the zero of the Vernier scale. So here, for example, if you look at this figure, this is your main scale. So this is my main scale. And this is the Vernier scale. So if I want to read my measurement, I look at the zero in the Vernier scale. The zero in the Vernier scale here is just between 3 millimeter and 4 millimeter. Okay, so I will take the number before to the left of zero, which is 3. So I have 3 point something. Okay, now to determine the figures after the point, I will look at the perfect match between the Vernier scale and the main scale. What I mean by perfect match, so I have two lines on the same level. So here, for example, this line is not matching with any of the graduation in the main scale. So I will try to go over the graduations, no match, no match. Here it is close, but not no, it's still no match. Okay. Here at 7, you have the perfect match. They are aligned. The two, the Vernier and main scale graduation are aligned together. While here you can see that here it's just we have a small difference. So 7 is the perfect match. So the reading here is 3.7 millimeter. Okay. Now the Vernier scale can be divided into a very high number of divisions. Higher is the number of divisions, higher will be the accuracy. So here, for example, what you are doing is you are dividing 1 millimeter, because here just 1 second, I lost the mouse. Okay, so here your small division is 1 millimeter, and on the main scale the smallest division is 1 millimeter, and you are dividing this division into 10 parts. Okay, so here this is 1 millimeter, and I can divide it into 10 divisions because in the vernier scale I have 10 divisions. So I can read up to an accuracy to 1/10 millimeter. Okay, so in case I have a higher number of divisions, so for example, if I have 100 divisions in the vernier scale, then I can read up to 0.01. I divide 1 millimeter by 100. Okay, so always I should look at the number of division on my vernier scale to determine the accuracy of my reading. Now, let us see some examples. Here, for example, in this vernier scale, I can read up to 0.01 millimeter. Why? Because look, 0.02, sorry. Why? Because I have here on the main scale, the smallest division is 0.1, is 1 millimeter. And this 1 millimeter is divided through the vernier scale into 50 divisions. Why 50 divisions? Because look, you have 0, 1, 2, 3 until 10. So you have here 10 divisions. And each division is divided into 5 parts. So here you have 1, 2, 3, 4, and 5. So you have 10 and 10 main divisions, and each division divided by 5. So you have 50 in total, 50 divisions on the vernier scale. So this means that I have 1 millimeter that is divided into 50 divisions in vernier scale. In vernier scale. So I can, the accuracy of reading will be 1/50. Okay, so I can read up to 0.02 millimeter. Okay, so in this case, what I will try to do, the method is the same. I will look at the perfect match. So here first, okay, this is my 0. I look at 0 of my vernier scale. It is just here. Now I will read here. It's 3 centimeter, 3.1, 3.2, 3.3, 4, 5, 6, 7. So until here, just at the left of 0, it's 3.7 centimeter or 37 millimeters. Now from the vernier scale, I will look at the perfect match. Here, they did a small zoom for you to see the perfect match. هلا هون it's not very يعني كتير قراب من بعض يعني you need to look very close to see the perfect match. هلا اكيد بالاكزام I will give you a clear figure like before. Okay, يعني بتكون الفيجر مبين ال perfect match. Here this is the perfect match. Okay, so I can read 37.4 and I have each division here is 0.02. So this is 42, this is 44, this is 46. So I read 37.46 millimeter. Okay.
دكتور
Yes.
فيها تكون perfect match مثلا مع ال 57 مليمتر
مع
لازم
ال
تكون إنه
57 فيها تكون وين ما كان فيها تكون ماتش مع من 0. اوكي معك انت من 0 لحديت 99 من بعد الفيرجول. اوكي يعني you can have possibility of match with any number. هلا بما انه انت السكيلينج تبعك 0.02 يعني فيها تكون 0 0.02 0.04 0. عرفت كيف؟ 2 بتمشي فيها لحديت 0.98. Yes.
Can you repeat كيف عرفنا إنه 0.02 بين كل وحدة؟
Yes. Okay. Your main scale is أصغر division بالmain scale تبعنا شو هي؟ هي 1 millimeter مظبوط؟ This is 1 millimeter. What is the idea of the vernier scale? Vernier scale will divide this 1 millimeter. It will divide it in a number equal to the number of divisions بالvernier scale. يعني higher is the number of divisions بالvernier scale, higher is the precision. فتتحدد بالvernier scale قد ايه accuracy, you should determine the number of division of the vernier scale. نحن هيدا الvernier scale تبعنا مقسم ل 50 divisions. Why؟ لأنه عنا في عنا main division اللي هن 1 2, 3, 4 up to until 9 و 10 آخر شيء. اوكي هول ال 10 divisions كل وحدة منهم فيها 5 division، يعني مقسمة ل 1 2 3 4 and 5. So in total how many divisions you have in your vernier scale? 10 times 5, okay, it is 50. Yani you are dividing 1 millimeter into 50 parts, so you are able to read up to 1 over 50 equals 0.02 millimeter. Okay, yani for example, if you have the perfect match here, if you have a perfect match at this level, what do you read? You read 0.02. If you have the perfect match here, 0.04, 0.06, 0.08, and 0.1, etc. Okay, here it's 0.12, 0.14, 0.16, 0.18, 0.20, etc. Okay?
Okay, thank you.
Well. Okay. Now, another example. This is another example here. Also, first, I look at the zero in the vernier scale. Okay? I have, this is 3 centimeter, 31, 32, 33, 34 millimeter here. Okay, just to the left of zero, I read 34 millimeter. Then on the vernier scale, I try to see the perfect match. Also here, I did a zoom for you. The perfect match is at 6. So it's just 34.6 millimeter. Okay. لو كان البيرفكت ماتش هون كان 34.62، لو كان هون كان 34.64 etc. اوكي هلا as I told you هون البيرفكت ماتش كثير صعب ينشاف لانه قراب على بعض كل القصص، بس انا بالاكزام بيكون كثير clear when البيرفكت ماتش. So just what I want from you is to understand the method, and in the exam the perfect match will be seen clearly in the figure. Okay. So this is for linear vernier scale. Now, for rotary vernier scale, what is the idea here? Here, the first significant figure is taken from the last graduation, showing on the sleeve directly to the left of the revolving symbol. Note that an additional half-scale division, 0.5 millimeter, must be included if the mark below the main scale is visible between the symbol and the main scale division on the sleeve. The remaining two significant figures, which correspond to hundredths of a millimeter, are taken directly from the symbol opposite to the main scale. Let me explain in detail what do I mean by that. So here, what do we have? Here, in the main scale, the division is even smaller. Okay, so you have, this is 1 millimeter, but you have here another division also here. This is 0.5 millimeter. So already your main scale, your smallest division in the main scale is what? Is 0.5 millimeter. So now the vernier scale, okay, the vernier scale will divide the 0.5 millimeter into small parts, okay, into several small parts. This is why what we do here, okay, for example, here we annotate the rotary symbol. We annotate it from 0 to 50. We have 50 divisions. Okay, this means that we are dividing 0.5 into 50. Okay, we are dividing the 0.5 millimeter, which is the smallest reading in the main scale. We are dividing it into 50 divisions. So we are able to read up to 0.01. Okay, we are able to read up to 0.01 in this case. So now, what we will do we will first, if in order to advance 1 millimeter, you need to do 2 complete rotations of your symbol. Okay, so the first thing to do is to look at the graduation just before the symbol. Okay, so here when you stopped, okay, what is the graduation just before your symbol? It is, you have 5 millimeter, you have 6, you have 7. Okay, so the graduation just before the symbol is 7. Now, so you read 7 point something. Okay, 7 point something. Now, it's point what? What I do now is I look at the perfect match between these two lines. Okay, the perfect match correspond to 38, because this is 35, 36, 37, 38. Okay, so now I have, this is 38 millimeters, okay, 0.38 millimeters. I add to it 7, so I have 7.38 millimeters. So I'm reading 7.38 millimeters. Okay, and now what I will do, I can see another example. Okay, in the other example, I look first at the graduation just at the left of the symbol. Here it is a lower graduation. So if I read, what do I have? This is 5, this is 6, this is 7, and this is 7.5. Okay, this is 7.5. This means that now I am reading 7.5 plus something. Plus what? I look at the perfect match between this line and the symbol line. So it is 20, 21, 22. So I am reading now 7.5 plus 0.22. Okay, I get equal to 7.72. Okay, any question on this?
Doctor, I have a question.
Yes.
Doctor, can you go up للصورة اللي قبل?
Up. Okay.
Yes.
Yes.
Yes, here doctor. Here ليه ما أخذنا إنه يعني 0.5 تكون يعني 7.5 لازم تقطع
لازم تقطع. Yes, exactly. لازم تقطع completely اللاين. اوكي، هلا انت كثير قريبه من الفايف. This is why بلشت تدق فيها بس بعد ما قطعتها.
اوكي، مشان هيك طلعت 38 يعني
exactly. طلعت very close، يعني بدها تبلش تقطعها. اوكي، وقتها تصير 0.5 بتصير عليها بالنص 100%، ووقتها تزيدي عن 5 تقطعها، بتبلش تقطعها. اوكي، رح فرجيكم هذا الشيء in the following measurements، هيك تقشعوها اكثر. هون مبينه اكثر. اوقات بتكون just على الزيح، اوكي، بس بعد ما قطعته على الاخر. how you make sure انه ما قطعته على الاخر؟ from the reading, from the matching. when you look at the reading here, it is 46، يعني بعد ما قطعت النص. اوكي، يعني هون انا على الزيح بس ما قطعته على الاخر، يعني بعدني ما صرت بنصه، يعني هو عنده شويه thickness. عرفتوا كيف؟ بس اوصل على نصه perfectly، يعني انا على ال 0.5. اذا بعدني قبل نصه شوي بكون قريب على ال 0.5. so here for example it's 1 2 3. بعد ما قطعت الزيح I read 46. so it's 3.46, very close to 3.5، يعني صرت تقريبا على نص الزيح. اوكي، while if I increase a little bit the measurement، يعني which is the case here، هون شفتوا كيف قطع الزيح، صرت اكثر من 3.5. so here when I read I have 1 2 3 3.5 plus something small، يعني هون مبين انه just قطعت الزيح. so I can read here 5 6. so it is 3.56.
دكتور إذا كانت between two line يعني إذا بالفيرنيير سكيل كانت between two line ناخد
ما بتكون على طول بيكون في ماتش. اوكي
يس اوكي. ودكتور كيف فينا نعرف اليونتس بالمين سكيل بالفيرنيير مثلا هون سنتيمتر؟
هن المفروض يحطوا لكم، يعني هن بس بحطوا لكم بالمين، وقت يعطوكم المين انتم بتستنتجوا الفيرنيير. عرفتي كيف؟ يعني انا اذا بحط لك هون مليمتر ساعتها انت بتعرفي انه هون عندي هيدي 1 مليمتر وهيدي 0.5. بس صرتي تعرفي انه اصغر ديفيجن بالمين هي 0.5، يعني انا هيدي 0.5 بقسمها على number of divisions بالفيرنيير بيطلع لي الاكيورسي تبع الفيرنيير سكيل. اوكي مثل ما قلنا هون عندي 0 اصغر measurement بالمين سكيل هي 0.5 ملم، وهيدي 0.5 ملم عم بقسمها على كم ديفيجن؟ عم بقسمها على 50 divisions. يعني I am reading what? I am reading up to 0.01. يعني كل division بهالفيرنيير سكيل هي 0.01 ملم.
Yes,
اوكي؟
doctor. Thank you.
نعم. Okay. Any other question? Okay. So this is for measurements using these scales. هيدا الفايل I will post it as I told you on Blackboard, and it will help you to do some practice. هول لازم تعرفون وهول شفتوهم بالفيديوز. Okay. So this is a practice on what we have seen in the videos. Now I will open a new session to start solving problems of chapter 3. Okay.
دكتور سؤال،
Yes.
نحن عندنا شيء الانش ولا بس مليمتر؟
هي ذات الشيء. انت شو فرقانه معك اذا انا بكتب لك هون انش او مليمتر؟ الريدنج هي ذات التكنيك. اوكي بس الفرق انه هون الفاليو بتكون ان انش، الفاينل فاليو بتكون ان انش، هون الفاليو فاينل فاليو بتكون ان مليمتر، بس الكونسبت از ذا سيم. اوكي فيني اعطيك سنتيمتر انا بكتب لك اليونت وانت بس تعمل الريدنج، انا بيهمني تعرف تقرا الفاليو.
اوكي دكتور، كان في بالفيديو حطيتيهم اكزامبل في 3 سكيل، عندنا شيء هيك نحن ولا
لا لا يعني انا بس هول الفيديوز تفرجيكم لانه رح تعوزون بعدين باللابس، قلت انه بعملكم انتروداكشن عليهم، بس انا يعني ككويستشن ما حاعطيكم مور، يعني هول هيدي المطلوب منكم بالنسبه للسكيلز مش اكثر.
ايه تبع الانش دكتور كان فيها 3 سكيلز.
هلا حلو تفهمون اوكي لانه بتعوزون باللابس حتشوفون في مانيفاكتشرينج لاب حتشوفوا كل هول التولز، بس يعني for this course يعني للبروبلمز اللي نحن حنعملهم we will limit ourselves to this. اوكي لانه اصلا اذا بدي اعملكم اياهم كثير صعب تشوفوهم هون على الفيجر، ما بتنشافوا، اجباري مثل الفيديو يفرجوكم اياهم. اوكي
ايه اوكي دكتور.
يلا so let me open a new session for you.